Hi, and welcome to part 3 of Vectors from A-Level Further Maths. I'm going to start with some recap. We've basically got 3 things to do today, which is going to look at angles and perpendicular distances. First, some recap. So we've basically seen this form for a line, and basically we have a position vector, which I'm almost think of as like a start point of 2, 1, 4, and this is a direction vector. So basically as lambda changes, we go in the direction of this vector. So on my crude sketch, you're going to see as lambda increases, you're basically getting further and further away from that start position. It's also worth mentioning, because I haven't done it explicitly yet, that R represents any point. So often you see R written as x, y, z. So it represents a combined x coordinate, y coordinate, and z coordinate. I've also looked at planes so far, and again we have 2 forms of a plane. We have this form here, which is quite easy to work out, and this form here, which is harder to work out, but really useful. There is a third form that backs onto this. So what I just said is R can be any coordinate of x, y, and z. And I can change that. And actually now I've got a dot product here. And we can work out this dot product. So we do 22 times x, which is 22x, plus 10y, plus 55z. And this is the exact same vector equation as this. All I've done is expand out my dot product. And this you see really common in like exams, almost mainly because it's easy to put on a single line of paper rather than being like a really tall vector. So if you do see it in this form, remember that the normal vector is given by these 3 numbers. So 22, 10 and 55. So occasionally you want to go back from this to this form here if you need to know what the normal vector is. Okay, so we just said that for this equation you have a normal vector of 3 minus 1, 2. Okay, and more precise, the whole equation would be that. Okay, I'm also going to explain quickly a few things a calculator can do that can be really helpful. It can basically do these 3 things. You can normalize vectors, sort of, and it can also dot and cross product. So I'm going to show you where those are. If we go on to run matrix, okay, let's normalize first. I think if you go to option, and if you then go across, sorry, if you go to option, then math vector, and then go across, you can see at the end we have a dot product, a cross product, and also norm for normalize. So say I want to normalize the vector. Let's exit this and go back to math vector. No. Go to math vector, and I can normalize the column vector. So say I had this column vector and I click normalize, it will then tell you what its magnitude is. So the magnitude of this is root 22. Not hugely useful, but it's useful to know it exists. Scrolling up, so again, go to option, vector, and scroll across. You have dot product and cross product. If I just scroll a bit, you can see what it's done from over here. You do cross product, put the 2 vectors in and press equals, and it'll work it out for you. Same with the dot product, that's kind of less use because it's so easy to work out the dot product. But they are there if you want them, just so you know. Okay, before I get started, one more thing to go through is what you're given in the formula book. So this is basically the formula section to all stuff and vectors. Basically the only important thing is highlighted. You're told how to do a cross product, or you're at least told this sort of determinant matrix trick, which it does save you a job. You're given some other stuff. This isn't really that useful. This we've kind of covered. That's basically alternate forms for equations of a line, but it's worded slightly awkwardly. Same with this, equation of planes is worded slightly awkwardly. What is useful is what's down here, and we're going to see that in a second. It's going to solve as a particular type of question, and it's so much easier if you're not seeing your formula booklet. Okay, let's actually get on with some questions. Part 1 is all around angles. So this, I think we've kind of seen in part 1, or the first part on vectors, sorry, and that's how to find the angle between 2 lines. So a typical exam question would go, here are 2 lines, part A, show the intersect. If you want to show the intersect, that means at some point, hopefully here, they cross each other and they're at the same point. So for part A, you would just solve line 1 equal to line 2. And you then pretty much just stuff it all in. And as I've said before, with these vectors, you can basically treat each line of it as a separate equation. So again, the top line represents the x coordinates, the middle the y coordinates, and the bottom the z coordinates. If these two lines are equal, then at some point they'll have the same x, y, and z coordinates. So we kind of want to break these apart. So if I look at my x coordinates, I'm going to have 3 plus 3 lambda equals 6 plus 5 mu. If I look at my y coordinates, I'm going to have minus 4 equals minus 4 minus 2 mu. And if I look at my z coordinates, I'm going to have minus 1 minus 2 lambda equals minus 3 minus 1 mu. Hopefully it's going to work. So we start with this one, which is the easiest. Here, these two minus 4s are going to cancel out. So you must be left with the fact that mu equals 0, which means I can cross off this and this. They both go to 0. We then look at my top line. I've now got 3 plus 3 lambda equals 6. That tells me that lambda equals 1. And then we use the z coordinate to check that. So for this, if we use the fact that lambda is 1 and mu is 0, the equation must still hold true. And that's basically your test. If this does work, then they do intersect. If it doesn't work, then they don't. So doing this, we have minus 1 minus 2 equals minus 3, with a minus 0 that we don't care about. And that does work. That is true. So therefore, the lines do intersect. And again, in tests, make sure you include this little line. I mean, it seems fairly pointless, but they want to see that you know that you finished the question, rather than you just got stuck and kind of given up and moved on without realising you kind of finished it. Also, really common question is you are asked to find the intersection point. That's the other way you do it. And if you were, you would get either line. This was easier. And just plug in what we know. So for this line, we know the fact mu equals 0. So therefore, the intersection point will just be 6 minus 4 minus 3. Okay, that was part A. That was a fairly straightforward example of that. Then for part B, we want to find the angles between the two lines. For this, you only care about the direction vectors. So the direction vectors tell us what direction they're pointing in, and that lets us give us our angle. That makes a line point in a particular direction. For this, we're going to use the dot product, which is A dot B is mod A mod B cos theta, where A and B are my respective direction vectors. So A dot B, that's going to be 3 times 5, 0 times minus 2, and minus 2 times minus 1. So it's 15 plus nothing plus 2. So that is 17. Mod A is going to be the 3D pi effect stuff on this. So it's 3 squared plus 0 squared plus minus 2 squared, which is the same as 2 squared, times by this, which will be 5 squared plus minus 2 squared, which is the same as 2 squared, plus minus 1 squared, same as 1 squared, times by cos theta. We can then rearrange that. Cos theta is just going to be 17 divided by these two fellas here. So 3 squared plus nothing squared plus 2 squared, that's going to give me root 13. And it's going to give me root 13. Then from there just go to your calculator and say theta equals cos to the minus 1 of this thing here. Okay. And yeah, that's pretty much it. There is a slight edge case, which isn't in this one. Occasionally, you'll get an answer greater than 90 degrees, like you might pick up this angle, and often it says find the acute angle. So sometimes you want to find this angle instead, and you just do 180 minus that, so that's pretty rare, but it does occur. Okay, on something slightly more interesting. So here we want to find the angle between a line and a plane. So in essence, I've got my line crossing here, and I want to find this angle here. And again, you have the same type of question. You would say, first of all, find the coordinate of the point where the line meets the plane. I'll start this, but I won't finish it because it's fairly straightforward. And this is slightly easier if you have this in this formula. It doesn't matter too much. And what we're going to do, we're just going to plug this into here. So again, x is my top row. So I've got 2 lots of 10 minus 4 lambda. Minus y, y is my middle row, so it's minus 15 minus 10 lambda. And then it's plus 3 lots of my bottom row, which is minus 2 plus 2 lambda. and that all equals 15. Then expand it all out and solve for lambda. Okay, that's very straightforward maths. I'm not going to go through it, so I'm sure you can handle that. On to part B, which is like more interesting part. We want to find the angle at which the line meets the plane. In other words, this angle here. And this isn't that straightforward. Okay, at first glance, you don't have anything straightforward to dot with, because what you want to do is basically you want to dot with this vector here, whatever it might be, and then do the same thing we just did in the previous question. But we can't if we don't know that vector. The only vector we know, and the one we're going to use, is going to be this normal vector. We know we've got a normal vector, which equals 2 minus 1, 3. And what we're going to do, we are going to work out this angle here. The reason we do this is because when the normal vector is always at 90 degrees to the plane. So if we work out this angle here, we can then work out this angle here by doing 90 take away x will give us theta, because normal vectors at 90 degrees to the plane. And then it's the exact same as the first example. Again, I won't go through all of it because I'm just repeating myself at this point. You write down the dot product. A dot B is mod A mod B cos theta. A is the direction vector, and B we're going to go on normal vector, and again these can go in either order, and then you just solve it from there. Okay, you then work out, this should be cos x, we'd actually put my diagram. You will then work out the angle, which is going to be this x here, and then you do 90 minus it. Okay, the key thing for these questions is you must do 90 minus the angle, and that's only when finding the angle between a line and a plane. Okay, the last thing we have to do is find the angle between two planes. Okay, so here we've got my crude sketch. We have two planes that intersect along this line here. And again, in case you have to find that equation of a line, that's quite rare. And we're going to find this angle between them here. Okay, we've got an equation for the two planes, but again, we only know the normal vectors. And we're going to do the same trick. Instead of finding the angle between the planes themselves, we're going to find the angle between the two normal vectors. So if we look here, I've got these two normal vectors, and if we do the whole dot product, if we do A dot B or N1, or the two ends dots of each other, we're going to find this angle here. And it turns out, you can kind of see from my sketch, this is a parallelogram, which means these two angles are equal to each other. So for this, it's quite straightforward. You just dot together your two normal vectors, and that will also give you the angle between the two planes. Okay, I won't go through that because it's fairly straightforward. Just make sure you dot each other to your two normal vectors rather than any other vectors. Okay, part 2 is on perpendicular distances. So you're required to find the perpendicular, often called the shortest distance between either a point in the plane, a point in the line, or two lines. And yeah, this is quite easy, and it gets steadily harder as we go down that list. So a point in the plane I mentioned earlier, we're actually given it in the formula book. So if we're going to find the distance between this point alpha, beta, gamma, and this plane, which is written in this slightly weird form, it's just this. And just to remind you, if you haven't seen it, these are modular signs, and they just mean take the positive value. So if this equals minus 4, you just pretend it equals 4. And the reason for this is that when you work out distance, it has to be positive. Like a distance of minus 4 doesn't make any sense. So you just say, okay, it's a distance of 4. I'll just give you one example of that. So we have our shortest distance between this point, which is going to be my alpha, beta, gamma, and this plane. I'm going to rewrite to put it in this form where it equals 0 on the right hand side. So this is the same as x plus 2y minus z plus 3 equals nothing. And now we can just use our formula. So the way it starts, you basically times together these numbers and add them all together, and then just throw your d at the end. So it's modulus of this times this, so that is 3, plus this times this, which is 4, plus this times this, which is 1, plus d, and d is 3, all divided by, and it's going to be the square root of all these numbers here. So the square root of 1 squared plus 2 squared plus minus 1 squared. and they come from these coefficients. So 1x, 2y, and minus 1z. And that's it. That's all you need to do. This added together gives me 11. And even because it's positive, I can get rid of the modulus signs. If it was minus 11, I'll set 11 anyway. And then we divide by this. 2 squared is 4, so we then have the square root of 6. And that's all you need to do. Really straightforward question. It's a mistake I always see. People kind of forget they have this formula book and tend to sort of try and use other methods that, of course, aren't really going to work that well. Next, we have the short distance from a line to a point. So I said earlier, we've got this line here where we've got some start point, which is our position vector. So in this case it's 2, 1, 4. And basically as we advance lambda, we move up and down that line. And I could extend this down here, where this will be lambda equals minus 1. So what we're going to do, I've got the steps up here. We're going to find the vector from r to p, which is going to be r minus p. So r minus p will be a vector that takes us from anywhere on r to p. This is awkward to draw because we have this thing here, lambda. So if lambda equals 0, r minus p would be this line here. If lambda equals 1, r minus p would be this line. If lambda is 2, r minus p would be this line, and so on and so forth. Okay, all of these are various forms of r minus p, just as we change lambda about. Okay, make sure you're okay with that. This is what we're going to use to get us to work at the answer. We want to find the shortest distance, which is also the perpendicular distance. So therefore, we want the value which is going to give us a right angle when it intersects with my original line. And if we want a right angle, we use the dot product. Remember, for two perpendicular vectors, if it equals 0, it means they are at right angles. And that's what we're going to do. And when we do that, we're going to get an equation which will let us solve to work out what value of lambda we have. I'm sure my sketch is horrendously wrong, so we're nowhere near lambda equals 2. But from my sketch, it's going to be a bit less or a bit more than lambda equals 2. Okay, let me actually go through that. So step 1, find the vector from r to p, which is just r minus p. So r minus p, I do this, take away this, so 2 minus minus 1 is 3, 1 minus minus 5 is 6, 4 minus 2 is 2, plus lambda minus 1, 3, 5. And again, as this lambda changes, where my line goes through this line is also going to change. So this basically represents all these lines at the same time. Next, we want to make sure that this line is perpendicular to this direction vector. So we're going to dot those two things together. And we want to dot this vector with the direction vector and solve it equal to 0. So we're basically saying that a dot b is 0, which means we're perpendicular, where a is my new vector of r minus p. Let me write that in sort of one vector. And we want to dot that with my other direction vector. Looks a bit strange. The way I remember it best is you're always going to have the same numbers here and here. Just in one case you have a lambda and the other case you don't. Okay? This is awkward to explain, sorry, it's the best I can really say, but hopefully that kind of makes sense. We're dotting this new line with the direction it goes in until we find out when they're perpendicular, which is when they equal 0. Let's go through the maths and see how it works. So top line, I'm going to get this times this, so it's going to be minus 3 plus lambda, plus, then do this times this, so 18 plus 9 lambda, plus, and then the last one is going to be 10, 2 times 5, plus 25 lambda. Okay, let's probably give a horrid number because I just made these numbers up, but let's go through it. So we add together our numbers, we have 10, 18 and 3, which is 25. We then have 25 plus 9 plus 1, so plus 35 lambda, and that equals 0. Okay, let's check quickly, that seems fine. And we're then going to solve that. So lambda is going to equal minus 25 over 35. Okay, which is minus 5/7, which is nothing nice. You can write it in a decimal, but as a rule of thumb we tend not to want to because that means it's around somewhere. We're not quite finished yet because the question said find the shortest distance. What I've done so far is I've worked out the value of lambda that will give me a perpendicular distance. However, it turns out that's all we pretty much need to do. That means when lambda equals minus 5/7, this thing here will give me the shortest distance from R to P, because this vector takes you from R to P. So substitute that in, and we're now going to have 362, and let me keep it out. So minus 5/7 of minus 135. What you now want to do is we want to find the length of this vector. Let me look a bit nicer. So you put it in the calculator if you want to, and that's going to give you something like, let's have a 7th out the front, and put this as fast as I can. That gives me this form, just going from here, so these things are exactly the same, which then simplifies down to 1/7 of 26. 42 take away 15 is something crazy, 27, and 14 take away 25 is minus 11. Okay, and that is the shortest vector from my line to my point. However, I want to find the distance though. Okay, if I now want to find the distance, we then have to use the whole 3D Pythagoras thing. And if you want, we can use our calculator actually. We can choose our calculator and use this norm button here and just type it all in here. So let's do that for a change of pace. So we have 26 over 7, 27 over 7, and minus 11 over 7. And there we go, that is the shortest distance, 5.58 square units or whatever. Okay, yeah, there's a lot to take in there, so let's read it really quickly. We found a vector from R to P, and again, that could be any vector, that could be any line, sorry, from anywhere on my line R to my point P. We then found what value we needed for lambda to make sure that was at right angles. So in step 2, we worked out what value of lambda would give me a right angled length. And all we needed to do was just find the norm of that vector, find the length of that vector to find the shortest distance. And that's it. Okay? So you write the vector, you then dot product it with its own direction vector. That will then give you the value of lambda. You then plug it in, and then you can work out the distance from the new vector you get. Okay, now moving on to short distance between two lines. I have a couple of things to go through. Definition: skew lines. Two lines are skew if they are not parallel and they do not intersect. So like most lines in 3D space are going to be skew. So for example, basically any lines you draw, these two lines are skew. Okay, so they're not parallel and at no point do they intersect. Next, we saw this in the first part, we had n hat. So again, n was a normal vector. If I have n hat, all that means it has a length of 1. Okay, and that is really important because when I explain the dot products, I sort of explain what it did, but there's kind of a better way to explain what it does. But this only works when we use unit vectors. So here I have the coordinates 3, 4, 5. So it basically represents a line, the vector 3, 4, 5 represents a line from the origin to the coordinate 3, 4, 5. So 3 squares in the x, 4 squares in the y, and 5 squares up. The dot product basically projects the vector in the direction of that unit vector. So by project, I mean it tells you how much it's pointing in that direction. So this is best with an example. If I do 3, 4, 5 dots with 1, 0, 0, so this here is a unit vector, so because its length is only 1. That's going to be 3 times 1, 4 times 0, and 5 times 0. So that has length of 3. All that's saying is that in the x direction, we're only pointing 3 squares along, which is really obvious to see. We're only going 3 squares in the x direction. I could also do the exact same thing. I could do 3, 4, 5 dotted in the y direction. That will basically pull out this number here, and that says I'm going 4 units or 4 centimetres, whatever, in the y direction. Which again, you can see really obviously, so I've gone 3 squares along, 4 squares in the y direction, 5 squares up. You can merge those together. So here I'm dotting it with this unit vector, so you can check this has a direction of 1, and this is basically saying how much are we pointing in the direction of the 3, 4 line. So how far do we point in this direction? And it turns out through basic Pythag, we point 5 squares along in that direction. Okay. I can change it around. So here this is still a unit vector, because this has length of 5, well, that's y over 1 over 5 here. And if I dot those together, you're going to have 3 times minus 4, which is minus 12, and 4 times 3, which is 12. So this equals 0. And we see what that means. That's going to mean that this is perpendicular. And if we look at the vector minus 4, 3, that means minus 4 across, and 3 squares in the y direction. And that is minus 4, 3, 0. And you can kind of see that that is going to be at right angles. And basically anywhere, if I sort of rotate this round like that circle, always going to be at right angles. And lastly, I could also dot it in the direction of the line itself. So here, if I dot this with its basically its own unit vector, I'll just tell me how long the line is. And in this case, this gives me root 50, which was the length of my original line. Okay, hope that makes sense. The key idea is that if we dot a vector with a unit vector, it will tell us how long it is in that direction. That is going to become super important now on the short distance between 2 lines. Okay, so here I've got these 2 lines. They do not cross, so again it looks like they kind of do, but like remember, if you look at 3D space, either might look like they cross, they in fact don't. And we're just looking at what is the shortest distance between those 2 lines. So here it's going to be somewhere like from there to there. And more precisely, we know to get a short distance, we must be at right angles to each of my 2 lines. That will always minimize your distance. To do this, if we say these are my 2 lines, we have this formula. The distance will be the 2 position vectors subtracted from each other, dotted with the unit normal vector. Okay, let me explain that really quickly. So, a2 minus a1 will basically be any vector from this line to this line. So let's say that's my vector a2 minus a1. Okay. Next, we don't want it in that direction, so that's just a random direction. We want it in the direction of my normal vector, because the normal vector is going to be the vector that takes the shortest distance. And then to do that, to work that out, all we need to do is to project this distance in the direction of the normal vector, which is where this formula comes from. It's basically saying find any line between the 2 lines and then dot it in the direction of the shortest distance. And that will then give you the short distance between the 2 lines. So, let's go through it. Let's give it some numbers. So often for these questions, they give you the vectors or planes in any form they want. I personally always like my lines in plane form. So remember, all of these equal lambda, and we can rearrange each one to give us lambda. So if I do that for x, so if I just ignore this time being, I'm going to get x is going to equal 3 plus 2 lambda. Okay, hopefully you can see that. And it's the same idea for y and z. For a shortcut, you actually taught us in the formula booklet, you basically flip the sign whatever's on the top. So it's going to be 3 minus 1, 0, and then it's plus lambda times by whatever's on the bottom. So in this case it's 2, 1, 3. Doing the same here. So flip the sign whatever's on the top. So 0, 3 minus 2. I don't want to use lambda twice, that can be confusing. So we use mu for our second unit, for our second direction vector. and it's the denominators, so 1, 2, 4. Okay, so our formula is going to be, we just saw, was the distance between the two position vectors dotted with the unit normal vector. So I'll call this R1 and R2, so this is A1 and this is A2. So A2 minus A1 is 0 minus 3, which is minus 3, 3 minus minus 1, which is 4, and minus 2 minus nothing, which is minus 2, and we want to dot that with a unit normal vector. To work out my unit normal vector, we've seen this before, we can do that by using the cross product. If we ever do the cross product, that will tell us what vector is perpendicular to both these two vectors. We'll use that when we found the equation of the plane. So let's go to my calculator. I want a cross product, and I then want to go back to just plugging in some vectors. So math vector, and I want two 3x1s. So I have 2, 1, 3, comma, another 3, 1 vector, which is 1, 2, 4. So working this out, this will give me a vector that is perpendicular to both. So if, let's write it down, we've done 2, 1, 3, cross with 1, 2, 4, and that equals minus 2 minus 5, 3. What we have there is we have n. That is a normal vector. However, it's not a unit normal vector now. So we can then normalize it. Again, this can go back to our calculator. I did normalize up here. Yep, there we go. And I can plug in those numbers, and that will tell me how big it is. So minus 2. Minus 5. And 3. There we go, so that is length of root 38, which is just 5 squared plus 3 squared plus 2 squared. So therefore my unit normal vector is going to be 1 over root 38 times by minus 2 minus 5, 3. And that's pretty much it. Like, this formula is awkward to remember, very hard to get your head around, but if you get those two things, or just are happy remembering it and using it, most of the work's done for you. So my distance is now going to equal, let's take 1 over root 38 out of the front, and now let's just dot those two vectors together. So any numbers, any common factors, you can always ignore when dotting things together. And lastly, it's come up in a second. Like with the previous question, we can't have a negative distance. So if we do get a negative answer, we're just going to take the positive value of it. So minus 3 times minus 2 is 6. 4 times minus 5 is minus 20. And minus 2 times 3 is minus 6. So this equals minus 20 over root 38. So therefore, my shortest distance is going to be the positive value of that. And again, as always in like exam stuff, make sure you kind of label it, make it really obvious that you know when you finish the question. Okay. And that is that. Okay, so a lot of sort of techniques to learn and be aware of. Most of them kind of revolve on the same ideas. And don't forget, for between a point and a plane, you have a formula to work it out. Okay, there are these questions to work through in the description. Hope that was helpful and good luck.